Hey everybody, your Friendly Math Tutor here with our Unit 4 Contextual Applications of Derivatives lesson part 2. So last week we went over all of the major concepts. This week what I want to do is just touch on each concept and do an example, more of like an AP type example for each of the topics that we talked about last week. All right, so as always, please subscribe, like this video, check out our Patreon. There's a lot of good stuff going on over there. Check out our TikTok, Instagram, Facebook, posting videos all the time. I'll be posting them all week related to more problems with this topic. So let's dive right in. So again, Unit 4 is the contextual applications of derivatives. So we're going to focus on rates of change. In last week's video, we talked about rates of change for straight line motion. Now we're going to look at kind of a different type of example. We'll get into some related rates. We'll do a little more L'Hopital's rule. We'll also do some more local linearity. They're kind of like the four big topics in Unit 4. So let's take a look at this problem. So this is an AP type problem. The wind chill temperature in degrees Fahrenheit, a human feels based on the air temperature, also in degrees Fahrenheit, and the wind velocity V is in miles per hour. So if the air temperature is 32 degrees, then the wind chill is given by this equation and is valid from V equals from 5 to 60 miles per hour. So for part A, we just got to find W prime of 20 and use the correct units. All right. So first, let's find W prime of V. And we're going to do that by using the power rule. Well, first here, the constant rule. The derivative of 55.6 is just 0. Now we've got to do 0.16 times negative 22.1. So I have that worked out here. That turns out to, actually, I don't. So we're just going to write it like this, negative 22.1 times 0.16 V, and then we're going to take 1 away from there. So that's negative 0.84. So this is the derivative. Again, you could multiply this out. I just decided to wait until we actually plug in 20. So W prime of 20 is negative 22.1 times 0.16 times 20 to the negative 0.84. And that ends up giving us negative 0.286. And that is in, so this is the point of going over this problem. So what we have is the wind chill is measured in miles per hour. The wind velocity is measured in miles per hour, and the wind chill is measured in degrees Fahrenheit. So what happens is the way our rates of change are going to work is it's always going to be the rate of change of the dependent variable over the rate of change, or the unit, I should say, of the independent variable. So this is going to be in the wind chill, degrees Fahrenheit, over, I should do that, over miles per hour. All right, and that's simply just because of, think of slope. Rates of change are slope. Slope is rise over run, so it's the dependent variable over the independent variable. So I might have said that oddly, but let me just say that one more time. It's the rate or the unit of the independent variable, it's the unit of the dependent variable, which in this case is W, so that's degrees Fahrenheit, over the unit or the rate of the independent variable, which in this case is velocity, which is miles per hour. All right. And then it just asked us to explain the meaning. So all this is saying is that when the velocity is 20 miles per hour, the rate of change of the velocity is this 0.286 in degrees Fahrenheit per mile per hour. So every mile per hour that it's changing, the temperature is going to change by this much. Okay? All right, so for part B is just finding average rate of change. So another reason I wanted to go over this problem was because here we have instantaneous rate of change, so we're actually finding the derivative. Here we have average rate of change. Average rate of change is like a slope of the secant line concept, which is more of like an algebra 1 slope concept. So for this case, the average rate of change is simply just going to be W of 60 minus W of 5 over 60 minus 5. So this is simply just substituting in. So I have it here, W of, actually, if you just plug this in, so you just plug in 60 to this and plug in 5 to this and then divide by 55, I just did the whole thing, then that ends up being negative 0.254. And again, it's the average rate of change. It's going to have the same unit as the instantaneous rate of change. So that's going to be degrees Fahrenheit per mile per hour. All right, so here is the instantaneous rate of change. Here is the average rate of change along the whole interval. All right, and the last part of this problem is now over this time interval from 0 to 4. They're telling us the air temperature is 32 degrees. That's useful just so that we're going to use this equation. And they say, what is the rate of change of the wind chill with respect to time? All right, but they're also telling us that the wind is 20 miles per hour and increases at 5 miles per hour. And when they want to know the rate of change with respect to time, they're asking us to do a related rate. So imagine we take this equation and we take the derivative, but with respect to time. So the derivative of W is going to be dW dt. And that's going to equal the derivative of this, which we already did. That's negative 22.1 times 0.16. times v to the negative 0.84. But we have to now remember, we're taking the derivative with respect to time. So whereas up here we could just stop because we were taking a derivative dw dv essentially. Here with respect to time we have to multiply by dv dt. So this ends up being negative 22.1 times 0.16 times something to the negative 0.84 times something, which is dv dt. So those two somethings is what I really want to talk about. That is going to be, so v is the velocity at a particular moment. So that's when t equals 3. So at t equals 0, the wind velocity is 20 miles per hour, but it's starting to increase at 5 miles per hour. So that means after 3 hours, it's going to increase to 35 miles per hour. So the wind velocity at that moment is really 35. And dv dt is the rate of change of the velocity. All right? So that is the 5 miles per hour. All right? So we multiply by 5 over here. If again you throw all of that into your calculator, we ended up just getting negative 0.892 degrees, and that is now in, degrees Fahrenheit per hour. All right, so the wind chill is changing, its degrees is changing, but now it's changing as a unit of time, and that's per hour. So notice the unit here is slightly different than the unit here. The wind chill, it's how it's changing, but here it's how it's changing with respect to the velocity, miles per hour. But here it's changing with respect to time, so per hour. All right, let's move on. All right, now we're going to take a look at some related rate problems. So this first one, a camera is filming the progress as a daredevil attempts to scale the wall of a skyscraper. The climber is moving vertically at a constant rate of 16 feet per minute, and the camera is 400 feet from the base of the skyscraper. How many radians per minute is the angle changing when the climber is 300 feet up the building? So basically we've got someone scaling a building here, we've got a camera out here, and it is pointed at where the climber is. Now we have an angle here that's changing, so I'm going to call that theta. The camera is 400 feet from the base of the skyscraper. Well, that 400 feet is not going to change throughout the problem. As the climber moves up the building, the angle is going to change, but the camera is going to stay positioned 400 feet away. So I can call this 400. It is a constant, not a variable. And then the climber is climbing up the wall, so I can just maybe call that x. So this is changing as the climber climbs up the wall. So now the relationship between those, I think we can see, is just tangent. So the tangent of theta is equal to the opposite, which is x over 400. I'm going to multiply each side by 400 and get 400 tan theta is equal to x. So that is our equation, and it's simplified as much as possible. So now we have to take the derivative of that equation. So this is 400 secant squared theta d theta dt equals the derivative of x is dx dt. And they want to know how many radians per minute. Well, radians per minute is simply just the rate at which the angle is changing. So everything else we should be able to figure out here. So we have 400 something squared, d theta dt is what we're trying to find, and then dx dt. So this something squared we'll find in a second. Dx dt is the rate at which x is changing, which they say is the climber moving vertically at a rate of 16 feet per minute. So that's 16 over here. So now this secant of theta that we're going to square. Let's take a look at this triangle. They want to know when the climber is 300 feet up the building. So that is when this value is 300, all right? It's only 300 at a moment, so we didn't call it a constant in the beginning of the problem, but it is a 300 at this particular moment. And if we see that this is a 3, 4, 5 triangle, then the hypotenuse is just going to be 500, again, at that particular moment. And if we have to find the secant of theta, well, the secant is the reciprocal of cosine. Cosine is the adjacent over the hypotenuse, so secant is going to be the hypotenuse over the adjacent, so that's simply just 5/4. So 5/4 is just going to go here. And now we can solve for d theta dt. So we get 400 times 25 over 16 is d theta dt equals 16. So we could probably just throw this in a calculator. I'm sure we could figure this out if we just simplified a bit. But I'm just going to use a calculator. So we've got 25 over 16 times 400 is 625. And then when we do d theta dt, it'll be 16 divided by 625. And that gives us about 0.0256. So d theta dt is 0.0256 radians per minute. That's the rate at which this angle is changing at that particular moment, okay? So that's just an example of a related rate problem that could have an angle in it. Now let's take a look at another related rate problem that has some geometric shapes, all right? So in the last video, check it out, we did a bunch of Pythagorean theorem problems and we did the prototypical cone problem. So now I wanted to do an angle problem, and the last related rate problem I want to do is just some geometric shapes. So we've got a circle and a square. So square inscribed in a circle, the radius of the circle is increasing at a constant rate of 0.8 centimeters per second. When the side of the square is 4 centimeters, what is the rate of change of the area of the circle? We'll just start with the area of a circle. So area equals pi r squared. As the circle is increasing, then certainly the radius is changing and the area is changing, so they're both going to be variables. Neither one is a constant. So I can just start by taking the derivative with respect to time. So dA dt equals 2 pi r dr dt. That is our derivative with respect to time. And dA dt is the rate at which the area of the circle is changing. So that's what we're looking for. So we have dA dt equals, we have 2 pi, we have the rate, the radius, and the rate of change of the radius. Well, the rate of change, they tell us right here, it's increasing at 0.8 centimeters per second. So that's 0.8. So the only thing we have to find is the radius at this moment. Well, the moment is when the side of the square is 4. So when this is 4, and let's say this is 4. And the radius we'll say is this. Well, I'm going to go all the way. So if this is 4, well, this is 4, and this is 4, then this is automatically 4 root 2, if you remember your 45, 45, 90 triangles. And if that whole thing is 4 root 2, that's just the diameter. So the radius is just going to be 2 root 2. So dA dt, the rate at which the area is changing, let's go back to the calculator here, and we're just going to do 2 pi times 2 root 2 times 0.8, and we get 14.217. And that, if we look at the units, well, this was centimeters per second, so it's the area, so it's going to be square centimeters per second. All right, so that again is 2 more examples of related rate problems. So now we're going to get ready to move on to the other topics in Unit 4. All right, let's move on to some local linearity. So this first one, f is a concave up on its domain. F of 4 equals 5, f prime of 4 equals 3. What is the estimate for f of 3.8 using linear approximation? So let's refresh the linear approximation formula. So L of x is f of a plus f prime of a times x minus a. All right, so that is something we went over in the last video. It just has to do with the point slope formula. So L of x just equals f of a. Well, a in this case is 4. Well, they just tell us these values. We don't have to plug them into anything. F of 4 is 5. F prime of 4 is 3. And then a is 4 itself. So if we want the approximation for 3.8, we're simply going to do 5 plus 3 times 3.8 minus 4. Well, that's just simply, well, 3.8 minus 4 is negative 0.2. Negative 0.2 times 3 is negative 0.6. And if we add that to 5, we should get 4.4. So that is our estimate based off of this given information. And then the other thing I want to go over is they'll say this a lot, and we'll see it again in this next problem. It's concave up on its domain, and we want to know if this value is an underestimate or an overestimate. So if you imagine, just picture a concave up function, and let's say you're trying to approximate this using local linearity, which is really just using the equation of the tangent line. Well, this tangent line, since it's concave up, is always under the curve. So any point that we use, let's say we're using this point to predict that point, well, it's going to have to be under because the line will be under because it's concave up. So you can just sketch this out. That means it has to be an underestimate simply because the graph is concave up. So let's take a look at another example. They give us this chart and they say the depth of the snow is given by S, all right, for between 0 and 12. But they're giving us a table of values for S prime of t, all right? And at t equals 4, the depth is 28 centimeters. Use local linearity to approximate the depth at 6. So again, let's use our L of x formula. So the first part of L of x is f of a. Well, we are going to use the value. So if we want to estimate this at t equals 6, the closest value on the table at 6 is going to be 4. So 4 is what we're going to use. And they tell us right here at t equals 4, the depth is 28 centimeters. So there's a couple clues there to use 4. So f of a is just f of 4. So that's 28 centimeters here. Plus now the slope, f prime of a. Well, f prime of 4 is we just use this table. That's 2. times x minus 4, x minus a, and a is 4 here. So if we want to evaluate, or we want to approximate at 6, we get 28 plus 2 times 6 minus 4. That's just 2. 2 times 2 is 4, and 4 plus 28 is 32. All right, so the depth of the snow would be 32 centimeters. And again, this one's saying that it's concave down. So if it's concave down and you picture a tangent line that's being used to approximate that curve, if it's concave down, the tangent line has to be above it the entire time. So therefore, it's going to just be an over estimate. All right, so the key here, the takeaway is please don't just memorize these two things. So if it's concave down, it's an overestimate. If it's concave up, it's an underestimate. Just to remember that concept, and you can at any time, you can just draw something that's concave down, or you can just envision this in your head. A line that you would draw that's tangent to it would have to be above it, so it's an overestimate, all right? Or if you draw something that's concave up, to draw a tangent line to it would have to be under it, so it's going to be an underestimate. All right, let's move on to our last topic. We're going to do some more examples of L'Hopital's rule. So if you watched last week's video, we talked about how L'Hopital's rule is used for limits that are either 0 over 0 or infinity over infinity. They are called indeterminate forms. That is because 0 over 0 is not what you would think. Maybe 0 divided by 0 could be undefined. It could be 1, right? So the idea is we're not actually dividing 0 by 0. We're dividing a limit that gets closer to 0 by another limit that gets closer to 0. So it's indeterminate. It's indeterminate because we don't know the rates at which they're going towards 0. And if they're going at different rates, we could get different answers. Same thing with infinity over infinity. That's not necessarily 1. 1 could be going to infinity faster or more slowly. And so we might get 1, or we might get 20, or we might get infinity, or we might get 0. So the idea is it really matters the rate at which they're going. So they're called indeterminate forms. There's other indeterminate forms too. So that's what I wanted to talk about today. So let's take a look at this first limit. The limit as x goes to 0. So if we analyze this, if we substitute 0 in, we're just going to get 1. And if we put 0 in here, 1 over 0 is really an infinite limit. So it's 1 to the infinity. So it'd be very easy to just say, oh, well, 1 to any power is 1, and just move on, and we'd probably be wrong. So the idea is this is indeterminate because, again, it's not 1 to the infinity. It's a number that's getting closer to 1 being raised to a value that's growing without bound. We don't know how that's going to, it's kind of like a tug of war. We don't know how that's going to like all shape out until we do a little bit more work. So saying that's 1 is not going to work. So here's how we do this. We're going to set this equal to L, and we're going to take the natural log of both sides. So the natural log of L is equal to the limit as x approaches 0 from the right of the natural log of 1 plus 3x to the 1 over 2x. And then we're going to use, the fact that we took the L on both sides was because we use this fact that we can bring this in front. So we're going to get the natural log of L is equal to the limit as x approaches 0 from the right of the ln of 1 plus 3x. And if I bring this in front, then that's kind of just be a 1 over 2x. So that 2x kind of just goes on the bottom. You're going to see this happen a lot. We want there to be a fraction so that we can use the original two forms of L'Hopital's rule. We've got these other indeterminate forms, but we can always change it in. So here, this is like the ln of 1, which is 0, and 2 times 0 is 0. So now we get the 0 over 0 form. So we're going to do L'Hopital's rule. So this is the same as the limit as x goes to 0. The derivative of this is 1 over 1 plus 3x times the derivative of 1 plus 3x, which is 3. And then that is all over 2. Now this is pretty easy. We can just plug in 0. This is 3 over 1 over 2. So the final answer, well, okay, the answer to this limit is 3 over 2. But we're not finished. I almost made that mistake. We have to remember we're solving for the limit. This is the ln of the limit. So the limit is going to equal e to the 3 over 2. That's the final answer to the limit, which is certainly not 1. So 1 to the infinity is not necessarily 1. So now let's look at the next example. Well, if we plug in 1 here, we get ln of 1 is 0. 1 over 0 is infinity when we're talking about limits. It's 1 over a really, really small number is a really, really large number. And this is also 1 over 0, which is another infinity. So now it'd be easy again to say, oh, well, infinity minus infinity must be 0. But it's not, because infinity is not a number. It's this concept that we're growing without bound. And one could be growing without bound more quickly than the other, or more slowly than the other, or at the same rate as the other, but just be off by like a factor. So we don't know how that's going to shape out. So we call it an indeterminate form. And just means do a little bit more work and do some algebra. So for this one, my algebra is going to be getting a common denominator. So I can multiply this over here. So I have x minus 1, multiply this over here over ln x, all over ln x times x minus 1. All right. So it's super important that we kind of, I'm kind of skipping some steps here, but I'm assuming we're in AP Calc that we can do common denominators pretty quickly. So now what I want to focus on is, imagine I plug in 1 now, I'm going to get 0 over 0, which is now a L'Hopital rule form. So I can do L'Hopital's rule. So the derivative. So the limit as x approaches 1 from the right, the derivative of this is 1, the derivative of this is 0, the derivative of that is 1 over x. On the bottom, I'm going to do the product rule. So the derivative of this is 1 over x times the second one, plus the derivative of this, the derivative of this, which is 1 times this, which is ln x. I'm going to simplify a little bit, I can see that when I plug in 1, I'm going to get 0 up here, and I'm going to get 0 both here. So I actually might as well, I'm actually going to do 2 things. So we are going to use L'Hopital's rule again, but I would rather on the bottom, actually I'll just do this also. Make that x to the negative 1. On the bottom, I'm going to distribute. So this is 1 minus 1 over x, which really is x to the negative 1, plus ln of x. All right, so really quick, just to recap, I feel like I was all over the place there. I know when I plug in 1 here, I'm going to get 0 over 0 again. So knowing that I'm going to take the derivative again, what I'm going to do is I'm going to rewrite the 1 over x to the negative 1, and I'm going to distribute this so I don't have to do the product rule again. Now I have individual terms, and the derivative should be much easier. So we're going to do the limit as x approaches 1 from the right. The derivative of the numerator is bring this in front, and I get 1x to the negative 2. On the bottom, derivative is 0. This is also going to be x to the negative 2. And plus the derivative of ln x is 1 over x. This is going to be 1 over x squared over 1 over x squared plus 1 over x. And if you just plug in 1, you're going to get 1 over 1 plus 1, which is just 1/2. So again, infinity minus infinity is somehow 1/2, right? So we wouldn't have known that. So you want to stay away from infinity minus infinity thinking that that's 0. Now let's look at one more indeterminate form. So if we take the limit as x goes to infinity, this is infinity. And 1 over infinity is 0, and the sign of 0 is 0. So again, we think, all right, well, infinity times 0 must be 0, because 0 times anything is 0. But again, those rules don't apply, because it's not, infinity is not a number. It's a function that's getting infinitely large, being multiplied by a function that is going towards 0. And it's basically, again, a tug of war of like what's going to kind of win out. So the way we're going to do this one is we're going to make it the limit as x goes to infinity. We're just going to think of this as the sine of 1 over 3x. And then I'm going to move this to the bottom. So if I move it to the bottom, it's going to be 3x to the negative 1. I just want a fraction. And now what happens is, again, I get 0 over 0. So I get one of the typical L'Hopital rule forms, and then we're going to do the derivative. So the limit as x approaches infinity. Well, and let me actually make this, just think of it as 3x to the negative 1. So we're going to do the derivative of sine as cosine. So it's the cosine of 3x to the negative 1 times the derivative of 3x to the negative 1, which is negative 3x to the negative 2 times 3. Don't forget that multiply by 3 chain rule. On the bottom, we're going to get the same thing. So I'm going to end up just canceling this out anyway because I just did this derivative. And then this whole thing is going to cancel with that whole thing. And now I'm taking the limit as x goes to infinity. Well, infinity to the negative 1, think of that as, I'll rewrite this, might be easier for you to see this. This is the cosine of 1 over 3x. Well, if you substitute in infinity, that's 1 over an infinitely large function, which is infinitely small, so that's 0. The cosine of 0 is equal to 1. And would you look at that? Somehow infinity times 0 in this case is 1. So they have a tug of war going, one's going to 0, one's going to infinity, and it's just all settling out at 1. So the whole point of this is there's a couple other L'Hopital forms, all right, that are, well, they're really indeterminate forms that are 1 to the infinity, infinity minus infinity, and infinity times 0. You don't have to memorize those. Just really have like a conceptual understanding of why they're indeterminate. And when you find something that's indeterminate, that just wouldn't always give you the same answer when we're looking at it from the perspective of functions growing towards infinity or growing towards 0. And you just have to kind of do some algebra. You always want it to end up looking like a fraction so that you get one of the two L'Hopital forms, which is 0 over 0 or infinity over infinity. Then you can do the derivative over the derivative, all right? So I hope that was helpful. That concludes our contextual applications of derivatives. We have 2 weeks worth of videos going over all of these topics. So again, check out our Patreon. We got some more cool things going on there. And check out our TikTok and Instagram, Facebook. There'll be problems going up there all week. And for one last time, I hope that was helpful.